In the autumn of 1988, as the Cold War entered its final and most structurally complex phase, Exercise REFORGER tested not only the speed of American reinforcement to Europe, but the cumulative maturity of NATO's transatlantic mobility doctrine developed over 4 decades. Because by that stage, alliance planners no longer treated reinforcement as a symbolic demonstration of solidarity, but as a rigorously quantified operational variable embedded within Central Front war plans. And REFORGER 88 represented the most demanding iteration of the series, designed to evaluate whether late-stage NATO could execute its final, fully integrated reinforcement architecture under realistic constraints involving rail congestion, seal-IFT sequencing, airfield throughput limits, and reception staging onward movement integration under simulated high-threat conditions. And unlike earlier iterations that emphasized simple troop arrival metrics, REFORGER 88 was structured as a systems test in which the arrival curve of U.S.-based units was deliberately synchronized with prepositioned equipment draw, rail dispatch windows across West Germany, and seal-IFT cargo offload timing at northern European ports, creating a comprehensive stress test of NATO's mobility chain from continental United States departure bases to forward tactical assembly areas near projected axes of Warsaw Pact advance. And planners structured the exercise to replicate late Cold War assumptions about Warsaw Pact mobilization speed, which NATO intelligence estimated could bring multiple first-echelon Soviet and East German armies to readiness within days, compressing the time available for alliance reinforcement, and requiring that U.S. heavy divisions be flown or shipped across the Atlantic, married to stored equipment, and moved by rail toward the inner German border within tightly modeled timelines measured in 72-hour increments, and therefore, REFORGER 88 incorporated detailed tracking of sortie, generation rates for C-141 and C-5 aircraft, tanker support allocation for transatlantic routing, port throughput measured in roll-on, roll-off vessel discharge rates, and rail network density expressed in train slots per day across the Bundesbahn system. Because previous exercises had revealed that the limiting factor in reinforcement was not aircraft availability alone, but the interface between arrival hubs and onward transport corridors. And in 1988, NATO planners deliberately saturated selected rail routes to test whether congestion at marshalling yards or bridge crossings would degrade movement tempo below war plan requirements, using empirical movement data to compare actual rail transit times against projected timetables embedded in defense planning documents. And seal-IFT timing was similarly scrutinized, as prepositioned stocks in Europe were sufficient only for initial force activation, with additional ammunition and heavy sustainment cargo arriving by sea, requiring careful sequencing between port discharge capacity and inland rail availability to avoid cargo backlog at docks, particularly in Bremerhaven and Rotterdam, where throughput was measured in vehicles per hour during offload operations, and airlift arrivals at Rhine-Main and Ramstein were monitored not simply for landing intervals, but for aircraft ground time, cargo pallet clearance rates, and personnel processing capacity per hour within reception centers, ensuring that RSOM procedures could sustain continuous flow without administrative pause. And the scale of REFORGER 88 reflected NATO's recognition that reinforcement realism required simultaneous stress across all mobility nodes rather than isolated demonstration of lift capability, and by integrating air, sea, and rail movement into a single operational timeline calibrated against hypothetical Warsaw Pact attack windows, the exercise became a final comprehensive validation of the alliance's reinforcement doctrine at a moment when political change in Eastern Europe was beginning to alter the strategic landscape, but operational planning still assumed worst-case conventional confrontation, and thus REFORGER 88 served as both culmination and proof, testing whether the mature NATO mobility system built since the Berlin airlift could sustain the arrival, integration, and forward movement of heavy U.S. combat formations under the most demanding conditions envisioned during the closing chapter of the Cold War. REFORGER 88 unfolded within a strategic framework shaped by NATO's late-stage defense planning assumptions, which by 1988 had incorporated more than a decade of refinement under the flexible response doctrine and subsequent air-land battle integration, meaning that reinforcement was no longer conceptualized as a slow buildup behind static defensive lines, but as a rapid, synchronized injection of combat power intended to complicate Warsaw Pact operational planning during the decisive first operational period. And therefore, the exercise planners deliberately structured REFORGER 88 around a compressed timeline in which U.S.-based heavy formations, including elements of V Corps and reinforcing divisions stationed in the continental United States, were required to deploy personnel by air within hours of simulated political authorization, while sealift vessels carrying follow-on sustainment cargo departed East Coast ports under a pre-sequenced schedule designed to align with European port discharge windows, and this sequencing required careful calculation of transit time across the Atlantic, measured in days at average convoy speeds of approximately 15 to 20 knots for roll-on roll-off ships, balanced against projected ammunition expenditure rates per division per day once units were committed forward, because any mismatch between sealift arrival and frontline consumption would create either dockside congestion or frontline shortfall, and therefore port capacity at Bremerhaven and Rotterdam was analyzed in terms of berth availability, crane lift rate expressed in vehicles per hour, rail siding density for immediate onward loading, and customs clearance efficiency for multinational cargo, all of which were integrated into exercise modeling, and at the same time the airlift component required continuous sortie generation from U.S. bases such as Dover and Charleston, with planners calculating aircraft availability percentages after maintenance rotation, crew rest compliance under long-haul flight cycles, and tanker support brackets positioned over the North Atlantic to sustain uninterrupted routing to European reception hubs. And once personnel arrived at Rhine-Main or Ramstein, reception staging onward movement procedures were measured against processing capacity targets expressed in troops per hour, bus allocation rates to move soldiers to prepositioned equipment sites, and draw time required to activate stored armored vehicles from climate-controlled facilities, with evaluators comparing actual activation intervals against doctrinal expectations that assumed units could become combat-ready within 72 hours of arrival, and the realism component of REFORGER 88 extended to rail movement stress, because Bundesbahn traffic density during peacetime already operated near high utilization on certain corridors, and exercise controllers inserted simulated infrastructure disruptions and priority conflicts to determine whether military train dispatch could be sustained at the required rate of multiple heavy equipment trains per hour along designated axes toward the Fulda Gap and North German Plain, measuring bottlenecks at bridge crossings and marshalling yards where siding length and signal sequencing could constrain throughput below war plan projections. And these data points were fed back into NATO mobility modeling systems to adjust reinforcement curves, ensuring that theoretical brigade arrival timelines reflected actual rail physics rather than optimistic scheduling assumptions. And by layering simultaneous airlift surge, sea lift discharge, and rail redistribution within a unified operational window, REFORGER 88 became less a symbolic show of force and more a quantitative validation of NATO's final Cold War reinforcement plan, exposing friction points in intermodal transfer while confirming the alliance's ability to generate sustained, synchronized flow from continental United States departure airfields to forward assembly areas in West Germany under conditions approximating those anticipated in a real European conflict scenario. One of the defining features of REFORGER 88 was its deliberate emphasis on late-stage mobility realism, meaning that exercise designers intentionally avoided the simplified assumptions that had characterized earlier iterations and instead introduced friction variables designed to replicate the cumulative strain of simultaneous reinforcement across multiple nodes. And this realism was most evident in the handling of rail movement, which had historically represented the pacing factor in NATO's ability to translate air and sea arrival into forward combat power, because while aircraft could deliver personnel rapidly, and ports could discharge vehicles at impressive hourly rates. The Bundesbahn network had finite train slots, bridge load limits, and marshalling yard capacity that determined how quickly heavy armored formations could be pushed toward the inner German border. And during REFORGER, 88 planners tracked train density per 24-hour cycle along critical corridors running from Bremerhaven and central German depots toward Hesse and Lower Saxony, comparing actual dispatch intervals against modeled requirements that assumed the movement of multiple armored battalions simultaneously, and evaluators recorded delays caused by signal sequencing conflicts, citing occupancy constraints, and priority allocation between civilian and military traffic, identifying specific bottlenecks at river crossings where bridge capacity limited simultaneous heavy transport passage, and the exercise also tested contingency rerouting procedures in which selected rail segments were treated as temporarily unavailable, forcing dispatchers to redirect military trains along secondary routes whose curvature and grade profile reduced average speed and increased transit time by measurable margins, thereby revealing the sensitivity of reinforcement timelines to infrastructure redundancy. And sea lift timing realism further exposed the complexity of intermodal coordination, because roll-on roll-off vessels arriving in staggered sequence required synchronized berth allocation, and any delay in crane availability or customs processing could create queuing that cascaded into rail scheduling windows, prompting exercise controllers to measure dwell time at docks in hours and compare those figures against doctrinal assumptions embedded in NATO's reinforcement planning software, while airlift arrival realism incorporated weather deviation modeling across the North Atlantic, requiring selected sorties to divert to alternate airfields and testing whether reception centers could absorb unscheduled surges without degrading processing efficiency. And throughout the exercise, NATO mobility staffs maintained continuous reporting on key metrics, including aircraft ground time in minutes, port vehicle offload rate in vehicles per hour, rail dispatch frequency expressed in trains per corridor per day, and equipment draw time per battalion in hours, generating a comprehensive data set that allowed planners to identify where theoretical reinforcement curves diverged from empirical performance. And this level of quantitative scrutiny reflected the maturity of NATO's final Cold War reinforcement doctrine, which recognized that deterrence credibility rested not on aggregate lift capacity alone, but on the precision of intermodal synchronization under stress, and by confronting real rail congestion, sea lift timing conflicts, and airfield saturation within a unified operational window. REFORGER 88 served as a culminating systems validation, revealing both the resilience and the friction points of an alliance mobility architecture built to sustain rapid, large-scale reinforcement at the most critical moment of potential confrontation in Europe. Beyond the quantifiable stress applied to rail corridors and port facilities, REFORGER '88 also tested the integration of strategic sea lift with pre-positioned equipment doctrine in a manner that reflected NATO's final Cold War planning assumptions about sustainment depth. Because while the personnel of U.S.-based divisions could be flown rapidly to Europe and draw heavy equipment from pre-positioned sites such as Pomkis depots in the Federal Republic of Germany, the sustainment stocks required to maintain those formations in continuous high-intensity combat for multiple days depended heavily on sea lift arrival sequencing, particularly ammunition, fuel additives, engineering equipment, and specialized spare parts that were not stored in sufficient quantity within forward depots. And therefore, planners incorporated into REFORGER '88 a detailed modeling of sea lift flow from East Coast embarkation ports, including Beaumont, Charleston, and Bayonne, calculating departure windows, convoy spacing, and Atlantic transit time against estimated daily consumption rates for armored divisions projected to expend thousands of artillery rounds and hundreds of thousands of liters of fuel during the first 72 hours of combat. And port operations in Europe were structured to mirror wartime surge conditions, with berth allocation prioritized for military cargo, roll-on, roll-off discharge rates tracked vehicle by vehicle, and immediate transfer to rail sidings coordinated to minimize dock dwell time measured in hours rather than days. Yet evaluators noted that even minor misalignment between ship arrival and rail availability created backlog at staging areas, demonstrating that the true limiting factor in reinforcement was not maritime capacity alone, but the precision of intermodal transfer. And this interdependence was further illustrated when exercise controllers introduced simulated delays in unloading heavy equipment due to mechanical issues with ramp systems, compelling mobility planners to adjust rail schedules dynamically and revealing how quickly congestion could propagate across the network. And airlift operations were similarly integrated into sustainment modeling, as C-141 and C-5 sorties delivered not only personnel, but high-priority cargo, such as command and control equipment and specialized munitions, with aircraft turnaround time monitored to ensure ground handling efficiency did not erode sortie generation rate, and reception staging onward movement procedures were evaluated not simply for personnel processing speed, but for equipment activation, realism, including inspection, fueling, and arming of stored vehicles, with activation time measured per company and compared against doctrinal assumptions that heavy battalions could be combat-ready within tightly defined windows. And NATO planners also assessed the cumulative impact of simultaneous reinforcement across multiple core sectors, recognizing that rail corridors feeding the North German Plain and Fulda Gap could become mutually constraining if dispatch schedules overlapped excessively, prompting discussion of staggered force introduction as a mitigation strategy within operational plans, and the comprehensive data generated by REFORGER. '88 therefore provided an empirical benchmark for NATO's final reinforcement doctrine, confirming that while aggregate lift capacity remained robust, the true determinant of effective combat power arrival lay in the alignment of sea lift timing, rail throughput, airfield processing, and depot activation within a synchronized operational timeline calibrated against projected Warsaw Pact offensive tempo, underscoring that the alliance's ability to translate strategic mobility into forward-ready divisions depended on precision at every node of the mobility chain. A central analytical outcome of REFORGER '88 was the recognition that rail bottlenecks, more than aircraft or ship availability, represented the most sensitive constraint within NATO's reinforcement architecture, because while strategic airlift and sea lift capacity had been expanded significantly during the preceding decade through fleet modernization and increased roll-on roll-off capability, the physical rail infrastructure of West Germany, operated within fixed geographic and engineering limits, including track density, bridge load classification, marshalling yard capacity, and signal sequencing intervals that determined how many heavy military trains could move simultaneously without causing systemic congestion. And during the exercise, NATO transportation, planners carefully recorded train dispatch intervals along key north-south and east-west corridors, noting that certain high-priority axes feeding the Fulda Gap experienced measurable delay when simultaneous arrivals from Bremerhaven and central depots converged on shared junction points, creating queue conditions in marshalling yards where siding length limited the staging of multiple armored equipment trains awaiting onward clearance. And these observations were compared against wartime modeling assumptions that had projected uninterrupted dispatch at specified intervals measured in trains per hour, revealing that even minor variations in dwell time at sidings or bridge crossings could expand into multi-hour delays cascading across the network. And exercise controllers deliberately inserted simulated infrastructure degradation scenarios, including partial bridge restriction and signaling disruption, to assess the resilience of rerouting procedures, demonstrating that alternate corridors often involved longer transit distances or lower permissible speeds due to track curvature and grade, increasing total travel time by quantifiable margins that compressed arrival windows at forward assembly areas. And these rail realism findings were particularly significant because NATO's final Cold War war plans assumed that heavy U.S. divisions would reach designated defensive sectors within a defined number of days after mobilization, meaning that rail delay directly translated into reduced combat mass available during the decisive opening phase. And sea-lift timing analysis reinforced this interdependence, as ships arriving at northern European ports required immediate rail allocation to prevent dock congestion. Yet if rail dispatch windows were saturated, port dwell time increased, tying up berth space and potentially delaying subsequent arrivals, a cycle that revealed the delicate balance between maritime throughput and inland transport capacity and airlift. Operations were also affected indirectly by rail congestion because equipment activation at POMCUS sites depended on rail-delivered ancillary supplies, and any lag in rail movement could slow final unit readiness even if personnel had arrived on schedule. And by capturing detailed empirical metrics, including average rail transit time per corridor, dwell time per marshalling yard, and deviation between planned and actual dispatch intervals, REFORGER 88 provided NATO mobility planners with a refined understanding of reinforcement friction at the precise moment when the Alliance's Cold War planning framework reached its most mature stage, confirming that while overall lift capacity was sufficient in aggregate terms, the decisive factor lay in managing rail physics and intermodal synchronization under stress. And this insight shaped subsequent analytical adjustments to reinforcement modeling, emphasizing staggered scheduling, expanded contingency routing, and prioritized corridor allocation as means to preserve arrival curves aligned with projected Warsaw Pact mobilization timelines during the final years of the East-West confrontation. Another critical dimension of REFORGER 88 was the evaluation of reception staging onward movement and integration under near-saturation conditions, because NATO's final reinforcement doctrine assumed that U.S. units arriving by air would draw prepositioned equipment, conduct rapid technical inspections, load basic ammunition stocks, and transition to forward movement within tightly compressed windows, often measured at 72 hours or less from initial arrival. And the exercise therefore subjected POMCUS sites and associated staging areas to sustained activation tempo designed to reveal administrative or mechanical friction that earlier iterations had not fully exposed. And evaluators tracked the time required to open sealed storage facilities, conduct inventory verification against automated logistics databases, refuel, armored vehicles, load communications equipment, and complete final readiness checks at company and battalion level, recording activation intervals in hours per unit and comparing them against doctrinal targets embedded in NATO planning documents, and in several instances minor discrepancies in parts availability or documentation sequencing produced measurable delay that, while small in isolation, accumulated across multiple battalions to compress forward movement schedules, demonstrating the sensitivity of reinforcement timing to procedural detail, and onward movement from equipment sites to tactical assembly areas relied heavily on rail allocation windows previously stressed during the congestion phase of the exercise, meaning that any delay in unit activation could disrupt pre-assigned train slots, forcing dispatchers to resequence movements and occasionally creating idle gaps in the rail timetable. An inefficiency that illustrated how RSOM processes and rail physics were inseparably linked within the overall reinforcement architecture, and airfield reception centers at Rhein-Main and Ramstein operated at sustained throughput, processing arriving personnel at rates measured in hundreds per hour, coordinating bus allocation to transport soldiers to equipment sites while simultaneously clearing cargo pallets from aircraft to preserve sortie generation rate, with ground time monitored in minutes to prevent cumulative degradation of the air bridge, and exercise controllers also incorporated simulated adversary disruption scenarios, such as temporary communications interruption or restricted airspace conditions to evaluate whether command nodes could maintain coherent situational awareness across the mobility chain. And the data collected during these RSOM stress tests reinforced a central conclusion that NATO's late-stage reinforcement doctrine was structurally sound, but dependent on precise synchronization between administrative processing, equipment, activation, rail dispatch, and sea-lift sequencing, because slippage at any node could propagate across the timeline and erode the cumulative arrival curve that underpinned deterrence modeling, and thus REFORGER 88 not only tested hardware capacity in terms of aircraft, ships, and trains, but validated the procedural architecture that transformed arriving personnel into combat-ready formations positioned along projected defensive sectors, confirming that the alliance's final Cold War mobility plan rested on a finely calibrated sequence of actions whose success depended on disciplined execution at every stage from airfield reception to forward rail deployment. A further analytical objective of REFORGER 88 was to measure sea-lift timing against projected ammunition expenditure rates under late Cold War combat assumptions, because NATO war planning in 1988 anticipated that armored divisions engaged in high-intensity defensive and counteroffensive operations could consume artillery, ammunition, anti-armor munitions, and fuel at levels that would rapidly exceed forward preposition stockpiles if sea-lift arrivals were delayed even by a matter of days. And therefore, the exercise incorporated detailed tracking of maritime transit schedules from U.S. East Coast ports, calculating estimated time of arrival against modeled daily expenditure curves expressed in tons per division per 24-hour cycle, and port operations at Bremerhaven and Rotterdam were evaluated for berth turnover efficiency, with discharge rates measured in vehicles per hour for roll-on roll-off vessels and container lift rate recorded in crane cycles per hour, while customs and documentation clearance procedures were deliberately compressed to approximate wartime priority conditions. Yet even under these optimized parameters, evaluators observed that synchronization between ship arrival and inland rail dispatch remained the critical pacing factor, because when multiple vessels arrived within overlapping windows, rail marshalling yards experienced queue accumulation that extended dwell time and risked cascading delay across subsequent arrivals, And this intermodal dependency reinforced a central lesson that maritime capacity alone did not guarantee reinforcement sustainability without corresponding rail elasticity. And exercise planners also examined the impact of staggered sea lift waves on forward sustainment depth. Modeling scenarios in which second-wave vessels were delayed by simulated weather or convoy spacing adjustments, revealing how quickly frontline consumption curves could converge with available stockpiles, thereby compressing the buffer between active combat units and supply shortfall. And airlift contributed to sustainment realism by delivering selected high-priority munitions and command systems that were time-sensitive, with aircraft ground-handling teams evaluated on their ability to transfer cargo directly to rail or truck within minimal turnaround intervals, reinforcing the importance of minimizing idle time at each node. And throughout the exercise, NATO mobility staffs compiled a consolidated reinforcement timeline, integrating aircraft sortie generation, sea lift arrival, port discharge, rail redistribution, and unit activation metrics into a unified dataset, allowing planners to compare projected brigade equivalent arrival by Day 3, Day 5, and Day 7 against modeled Warsaw Pact mobilization timelines. And this comprehensive synchronization analysis confirmed that while NATO possessed sufficient aggregate lift assets to meet reinforcement targets, the decisive determinant of operational effectiveness lay in the precision with which sea, air, and rail movements were sequenced to maintain continuous sustainment depth, highlighting that the Alliance's final Cold War reinforcement plan was a complex choreography whose credibility depended on disciplined intermodal timing under conditions approximating the most demanding scenarios envisioned during the East-West confrontation. By the conclusion of REFORGER 88, NATO planners possessed the most comprehensive empirical dataset ever generated on the Alliance's ability to execute its final Cold War reinforcement architecture under realistic stress, and the exercise confirmed that while strategic airlift and sea lift capacity had reached levels sufficient to move heavy U.S. formations across the Atlantic within projected timelines, the decisive variables governing combat power availability remained the precision of rail throughput, the elasticity of port-to-rail transfer, and the synchronization of reception staging onward movement procedures with pre-assigned dispatch windows, because reinforcement success was measured not simply by arrival at European soil, but by the moment when fully equipped battalions reached forward assembly areas, aligned with defensive sectors. An analysis of cumulative arrival curves demonstrated that minor delay at any intermodal node, whether an aircraft diversion increasing ground congestion, a roll-on roll-off discharge backlog extending dock dwell time, or a marshalling yard bottleneck constraining train frequency, could compress the margin between projected NATO combat mass and anticipated Warsaw Pact offensive tempo, reinforcing the doctrinal insight that deterrence credibility depended on managing friction across the entire mobility chain rather than maximizing any single transport mode, and the rail congestion findings in particular led to refined modeling assumptions, emphasizing staggered scheduling and prioritized corridor allocation in subsequent mobility planning. While sea lift timing analysis reinforced the importance of phased sustainment waves aligned precisely with projected ammunition and fuel consumption curves, and RSOM performance metrics validated that late-stage NATO had achieved high levels of administrative and technical efficiency in activating prepositioned equipment and processing. Arriving personnel, though with recognition that procedural discipline remained essential to prevent cumulative slippage. And thus, REFORGER 88 served as a culminating validation of the Alliance's reinforcement doctrine, at the moment when geopolitical transformation in Eastern Europe was beginning to alter the strategic environment, confirming that NATO's 4-decade investment in integrated airlift, sea lift, rail coordination, and infrastructure resilience had produced a mobility system capable of executing the most demanding reinforcement scenario envisioned during the Cold War. Even as the confrontation that had necessitated such meticulous planning approached its end, and in this sense, the exercise represented both the final stress test of NATO's Cold War reinforcement design and a quantitative demonstration that the alliance's deterrent posture rested on a deeply integrated, empirically validated mobility architecture calibrated to deliver sustained combat power across the Atlantic within tightly modeled operational windows.